Hey, everybody. Thanks for having me here. So as you had mentioned, I'm Paul Dix. I'm the co-founder and CTO of InfluxData. We build a time series database called InfluxDB. So time series is useful for storing metrics, sensor data, events, and really observational data of any kind for physical systems, virtual systems, servers. So in this talk, I'm going to talk about how we created great storage savings and much, much better performance in the latest version of our database, 3.0. So first, let me talk a little bit about InfluxDB, how long we've been around. So we're an open source project and also a commercial product. The first commit of InfluxDB was a little over 10 years ago. The first release was shortly after that. And over this time, we've tracked the usage of InfluxDB over time. So here we can see 900,000 active instances. Those are basically open source servers running out there in the world. We've had over 100,000 signups to our cloud platform. And of course, GitHub stars. What open source project doesn't track that? So why did we actually build a database for working with time series? The first and most obvious one, answer is to deal with scale. When you're tracking a lot of sensor data or a lot of things in a bunch of different servers, it's very common to have hundreds of millions or even billions of individual records per day. In a traditional OLTP database, this is difficult to deal with this much data. For us, real time is also a very important component. Obviously, when you talk about scale, people are very familiar with their data warehouses and big data systems, but for us, real time means data has to be queryable as it arrives, basically within milliseconds or seconds. And for all the queries we're executing, they have to return many times in sub-second timeframes so that you can show real-time dashboards and you can build monitoring and alerting and systems that take action based on this data. And then one of the other challenges with time series data in particular is this idea of cardinality, which is with time series data, you have different dimensions along which you want to slice and dice that data. And as the number of dimensions increases and the number of unique values in those dimensions increases, that increases the cardinality of the total number of series you have. And in time series databases, this has traditionally been very, very hard to deal with. So we spend a lot of effort over the evolution of InfluxDB to try and optimize these things. So here is our rough timeline. We released version 1.0 of InfluxDB in 2016. As I mentioned, the first commit of InfluxDB was in 2013, over 10 years ago. So it took us 3 years to get from that initial commit and prototype up to version 1.0. That was written in Go, and I would say it was a database that was optimized for the metrics use case, right? For sensor data use cases where you're tracking individual metrics and pulling back that data. And we iterated over time. We released that as a cloud product on AWS and as an on-premise offering that people could buy and run themselves. Now in 2020, we released version 2.0 of the software. Now with that, we tried to expand it from not just being a database, but being an entire time series platform for doing other things. We added a custom scripting language so that you could define more complex processing and analytics inside the database. And we added a system for running tasks, which is basically periodic things that the database would run to do monitoring and alerting or to do transformation of the data. And we released all of this as a usage-based platform that we track on different metrics. So we basically had it as a cloud-first delivery of a product that previously we'd been shipping only periodically, like 3 times a year as a software product. Now, right around the time we released 2.0, we started thinking about what we wanted to do with the next version of the database. And for that, we really wanted to tackle some of the core database challenges that we saw. So we got to 3.0 this year. We had the first couple of releases, serverless platform in January, our cloud dedicated platform in April, and our on-premise release a few months ago. And this time, we built a real-time columnar database that could do not just time series, but also real-time analytics. So let me talk a little bit more about why we developed InfluxDB 3.0. So we realized over time that a columnar approach, a columnar analytics database would be much, much faster for doing analytics queries. But in 2020, when we looked at the space of columnar databases, we couldn't find anything that was specifically optimized for working with time series data, and one that was built specifically for the cloud, right? Using dynamically scalable compute tiers paired with cheap object storage. So with 3.0, our goal was to do just that, to tackle all of those problems. So key to all of this is the different tools that we used to build 3.0. Now I mentioned before, version 1 and 2 of InfluxDB was written in Go. With 3.0, we did basically a ground up rewrite of the database because we were changing the core architecture. And we used the Rust programming language. And we picked it specifically because of memory safety, speed, fearless concurrency, the error handling, crates, and all the other advantages that Rust provides. We also chose Parquet as the file persistence format, and that we would keep those files in object storage. What that meant was we could decouple the ingestion tier, the query tier, the compaction tier from the actual persistence layer, and because it's Parquet files in object storage, we would get much better cost efficiencies and potential integration with other systems. We used Apache Arrow as a memory format for data, for columnar in-memory data, so that we could do fast interchange between the different components of the stack. We picked Arrow Flight SQL as the network mechanism for clients making calls to the system, executing queries, and getting data back quickly. And then finally, we picked the Data Fusion query engine, which is a SQL parser, planner, optimizer, and execution engine that's written in Rust. So let me talk a little bit more about each of these individual components. First, Apache Arrow. So this is a project that was founded in 2016. Originally, it was built to basically share data quickly and cheaply between different data science work stacks, right? So basically they wanted to be able to share data science data sets between Python and R and other big data systems without having to spend a lot of compute time on serialization and deserialization. It's a top-level Apache Software Foundation project, and it's a low-level foundational technology to build and interoperate with analytic systems and data science systems. It's an open standard with implementations in 12 different languages. So all the popular languages have implementations of Apache Arrow. The one we work with in InfluxDB 3.0 is the Rust implementation, and we're heavy contributors to it. And it's adopted widely in industry products and in other open source projects. So it's quickly becoming a way to exchange data between different systems, which is really great. So now let's talk about Data Fusion. So Data Fusion is a native, like I said, SQL execution engine that is written in Rust. It's a sub-project of Apache Arrow. As I mentioned, it is a SQL engine, and it uses the Postgres dialect to do its SQL parsing and execution. But it is all in Rust, so you have like a completely new implementation of it. It's a columnar engine, and it's vectorized, so you get a lot of performance benefits out of that. It is basically best in class in terms of executing analytic queries on these kinds of data sets. Now, the thing we like to talk about with 3.0 is that it enables massively more storage at reduced costs. And the reason for this is, as I mentioned, we use Parquet as the storage format, and we use object storage on the back end. So for us, the differences between version 1 and 2 of InfluxDB and version 3. So in version 1 and 2, they're built around our own custom storage engine called TSM. So we created a storage engine to be able to compress time series data. Now, when we switched over to using Parquet for version 3, what we saw is about a 4 to 6x reduction in disk storage, in disk space. That, combined with the fact that we're now using object store as the long-term data store, which is much, much cheaper than an EBS volume with provisioned IOPS. Parquet as a persistence format also enables interoperability. All the big data warehouses are able to give you data back in Parquet and ingest data as Parquet. So Redshift, Snowflake, Databricks, and all sorts of data science tools like Pandas and R are able to actually read Parquet files directly, which is a great way to transfer data in bulk. This is part of what the company Voltron Data has been talking about as the open data architecture. And Parquet is one of the building blocks for that, to be able to interchange data in bulk between all of these different systems. One of the other things that was really difficult to get with 3.0, one of the, I think, the kind of secret sauces of it is it's easy enough to build a query engine that's going to suck in data from object storage and give you an answer. But it's really hard to get it to do that and answer queries in less than a second. So a lot of the infrastructure we built in 3.0 is basically a way to manage the data lifecycle as you ingest the data in real time, keep it in memory, buffered, and available for query, while at some point you later persist it as Parquet files into object storage. And then you have a query execution tier that has to be able to read data from object storage and know what to cache and keep on a local disk to be able to answer all of these queries very, very quickly. So InfluxDB 3.0 is optimized basically for answering queries against that leading edge of recently ingested data in less than a second. And again, for our use cases, this is very important for real-time dashboards, for automation and control systems, and monitoring and alerting. But at the same time, InfluxDB 3.0 enables faster results even with larger data sets. And again, this is because of that data fusion query engine. It's vectorized execution, it's optimized I/O, where we can push down processing into the actual Parquet reader so we know which columns to decode and which not to decode. And we have different ways of partitioning the data to make sure that when a query comes in, we can view which partitions are applicable to the query and only execute against those versus the entirety of data that's in the database. And all of this is paired with an execution engine that is able to parallelize across many cores and use as big of a server as you have available. So with 3.0, our goal was, before with InfluxDB 1 and 2, what we had was a great metrics database for time series. We wanted to be able to expand that into raw events and other high-dimensional data. Really, any kind of observational data you can think of, you can store and query within InfluxDB and do it at a much lower cost. So we did some comparisons of version 3.0 of InfluxDB compared with previous versions. And what we saw was on equal size hardware footprints, 45x better write throughput, or basically you're using fewer CPUs and less RAM to ingest the same amount of data. A 90% reduction in storage cost, which is a result of the reduced size in disk and also the cheaper object storage, and much, much faster queries on high cardinality data. For queries that have to hit many individual time series, InfluxDB 3.0 is way faster than previous versions. There are queries that 1.0 and 2.0 won't even process. They'll just time out. The 3.0 will easily handle in milliseconds. And faster queries, again, on that recently ingested data, that leading edge. So this is what the 3.0 product suite looks like. We have our data collectors, and we have our different query languages. We support both both SQL and InfluxQL. We have our API, which is the version 1 API, both write and read, the version 2 write API, and soon version 3 APIs, and also Flight SQL. All of this on top of the time series database. We offer this in AWS as the cloud serverless platform, which is basically smaller workloads where you just pay for data in, number of queries that you execute, and data at rest. We launched Cloud Dedicated, which is dedicated resources spun up on demand for customer for cluster. So it's basically a cluster where we help you size it, and it can scale up and down dynamically, and it's a managed service that runs in any AWS region. And then clustered, which is our on-premise, you run it yourself, we give you the software, and that's designed to be run inside a Kubernetes installation, either within your own data center or any cloud provider. So to find out more, go to influxdata.com and you can get started, get more information. And I will be around at the conference. I'm happy to answer any questions. I will be at our booth, I believe it's 552, tomorrow morning and Wednesday morning as well. So thank you.